Okay, let me restart. Now, if you remember, we were basically here to discuss that this vector here isn't a vector which lies on the plane x, y, it is orthogonal to this set here, but is included in dimension in a space of dimension 3. I don't know if this what I told you now is clear. This vector here is orthogonal to this set here, but is included in the room with dimension 3 because of also this dimension here. If I write, please, in order to understand, comma 0, not a 0, I mean 1, 1, 0, comma 0, this means that the vector 1, 1, 0, 0 is again orthogonal to this set here, but included in the dimension 4. It's as if I have another point of view. I enlarge my point of view. Now, coming back to our original, otherwise we cannot proceed. As I told you, this is orthogonal, as is written here, to this here, but in 3 dimensions. But this vector here is orthogonal also to Z. This vector here characterizes the axis Z. I don't know if it's clear that 0, 0, 1 is a vector which lies on the z-axis. I don't know if it's visible. 0x, 0y, but 1z, of course, could be also 10z, could be also whatever you want. But typically we consider one, excuse me, because we consider the unit vector. This means the vector with norm 1. Now, if you look at the vector Vz and the vector Vl, and if I do the dot product, I don't know if it's visible, but I have does this dot product equal 0? This means Vz is orthogonal to Vl. Clear? But VL was orthogonal to the set here. This means the z-axis as a set of points is parallel to the plane in 3 dimensions characterized by x plus y equals 100. See, pay attention to this, otherwise I can write. This VL is orthogonal to the set x plus y, this vector here. Yeah, this vector here is orthogonal to the set x plus y equals 100 in 3 dimensions. Now, the vector 0, 0, 1, or the Vz, is orthogonal to VL. This means Vz is parallel to the set or the plane, but to say set characterized by x plus y equal x in 3 dimensions, which is the plane. I don't know, should I write? Look at I don't know if it's able to simulate what I intend. Excuse me, in 2 dimensions. This finger is orthogonal to this one. Right? Now, if I am considering this direction, the blue direction, which is orthogonal to this, is parallel to this finger here. This is the idea. It's a little bit more complex because we have a plane, we have a set within a plane. Should I write this? But I don't think so. I write it quickly. So think about at home, and then we have to do the exercise. This means it follows that Vz is orthogonal. Let me write, so we write quickly, to this set x plus y equals 100 in 3 dimensions. which is in a plane. No? Okay, let me go ahead with this. That was a little bit to repeat a little bit what we have seen. How we can now go ahead with the exercise to find this minimum. Now, we know, in particular, if you look at the picture, that we are looking for a minimum because the intersection between this surface and the red plane is the minimum. I don't know if we can see. Do you remember this is a hillside? This is not a hillside. Is what is the country of hill? In Germany, Tal, no? In English, I don't remember. It doesn't matter. It's clear what I intend. No? The intersection is something which, yeah, which we can see here. Because maintain the let me say, the shape somehow of the surface. Valley, no? In English, is valley, right? Something like that.
Valley is
It's hard, yeah? So something like that. Okay. Now, building, do you remember the Lagrange function? Do you remember I tried also to tell you about the meaning very quickly? This means the function, which I want to minimize, combined using a parameter with the constraint. If you remember, I already told you a little bit graphically also, or starting from a graphical interpretation, why where the idea of the theorem comes from. It's easy to remember. If you don't remember, I write in the data sheet for the exam, fx comma y minus or the plus. In some books you can find plus, but we use minus lambda. We multiply the constraint x plus y equals 100. Now, explicitly, as I told you, is here. Now, gradient. The gradient means the vector of the Lagrange. We can say the gradient of the Lagrange equals 0 to find the candidate points. The candidate means could be minimum, could be maximum, could be also saddle points. We will see in the examination, we will find just minimum and maximum. For the saddle point, we have to do too many calculations. If you remember also in math, with the second derivative with the with the even derivative, we characterize the maximum and minimum. With the odd derivative, we characterize the flex of saddle point. Here we are looking for maximum minimum. But of course, the idea is quite similar. No? We have to go ahead with the derivative. I don't know if it's clear now the gradient here. The gradient of this expression here in terms of x, y, and lambda, which is a supplementary variable, is 2x minus lambda. Why that? Because the derivative with respect to x is 2x minus lambda. Then we have the derivative with respect to y, which is 4y minus lambda. We can see from here. No? And here is the derivative with respect to lambda, which is minus the constraint. The gradient is clear, no? The partial derivative. Once I do the derivative with respect to x, once I do the derivative with respect to y, and at the end, in this case, at the end, I do the derivative with respect to lambda. Now, putting these three components equal 0, I try to find the candidate or the points, which could be maximum, could be minimum. First component equals 0, second component equals 0, third component equals 0. Please pay attention. Here is relatively easy to find, but it could be also impossible to find or to do or to find the solution. Why it could be also impossible? Because depends how complex is this L. Because now in this case, we have a linear system. Do you know the difference between linear and nonlinear a little bit? If I have x squared cosine of x, I will come back on linear nonlinearity a little bit more precisely in January. In Gymnasium, we solve the linear system. When we don't have, we have just, let me say, the exponent of the variable is 1, x up to 1, lambda up to 1, no multiplication between the variables. In general, not roots. This is linear. Let me say linear. I will characterize properly the system or the linear system. Now, I have 3 equations we can see here, and 3 unknown, x, y, and lambda. If the system is linear, we can find the solution. Could be 0, 0, 0, could be another value. Depends. This depends. Yeah, how I can solve from Gymnasium. From the first equation, lambda here is equal plus 2x. If I plug in lambda here in the second equation, I have 4 lambda minus 2x equals 0, which implies y equals x divided 2 from here. From lambda equals 2x, plug in here, I have y equal x divided 2. And now I can plug in the first one, and I have x plus x divided 2 minus 100 equals 0. This means x at the end is 200 divided 3 from here. This means y from here is 100 divided 3, because it's x divided 3. And this means that I already have a candidate point. Of course, graphically, I know that is a minimum. This means the calculations using the bordered Hessian matrix, even though could be relatively complicated, but I know that should reflect that the point 203, 103 is in the minimum. Basically, with this point here, I didn't put it. I have to consider here the projection, and it should be for x 200 divided 3, and for y 100 divided 3. At this point here, if you do the projection in order to find the coordinates, the minimum is here, but I am looking for its coordinate, which is the number of product x per day, which is the number of product y per day economically. It's a little bit abstract, but you can understand what I intend. I have a software also, but I don't have time to show you the software. It's a software which can be used also for more than 2 variables. Of course, if you have more than 2 variables, it's extremely complex. If I have a function f of x extremely complex, we cannot solve manually. It could be that I need numerical method. Do you remember in this lecture, I told you again, I would like to tell you again, there is a point numerical methods, which I don't have time to tell you. But now you understand what I intend. If this system is not directly solvable, now it's easy to do. I will show you later something which I never pretended in the exam. But in order to inform you, that could be also impossible to solve analytically. We need a computer. Okay, we were here, no? Now, this point here is in particular with these 2 components, because this component here, lambda, this is the lambda. this 2 times x. No? This means instead of 200 divided 3, 400 divided 3. This no meaning for us. It's just a mathematical meaning, which is the parameter for the parallelismus. Do you remember? Between the gradient of f is the gradient of g. If you don't like, forget. But if you look again at the lecture in order to recall the idea of the Lagrange came from the concept that at the point, do you remember the lecture? At the point when the side hill meet the level curves, I don't remember this concept here. The gradient f is parallel to the gradient of g. If you want, I can insist on this. Okay, look now. This no practical meaning. Okay, the practical meaning is what I told you. Yeah, exactly. The point for us is this. How many x per day? X is the number of elements which I have to produce. It doesn't matter which category. I told you TV, radio, I don't know why. Probably better diodes and transistors in electronics. And this is the number of Y. Intuitively, we can understand. It's an extremely easy example, didactically relatively easy. Because do you remember, both the cost were squared, but the cost of Y, the weight of the cost of Y were twice of the weight of the cost of Y, of the cost of X. Like this is reflected also in the solution. I don't know it is clear what I intend. If this is the cost, of course, practically, I don't know if you have more experience than me. The cost of production sometimes is extremely complex with sign cost, extremely complex. Because very often what I have seen, this is just an didactical example, but both products, in this case, the cost per day is squared. The difference is just this factor here. I'm not surprised if I see as a possible solution that I can produce twice x with respect to y, because the cost of x is half, roughly speaking. Look, border Hessian. You don't remember? It does not matter. You can find the data sheet, because sometimes I don't remember me too. But the concept is an extension of a Hessian matrix. The Hessian matrix is known Hessian matrix, the matrix of the second derivative. Forget. In gymnasium, it's clear, no? First derivative, second derivative. The second derivative was used to classify if it's minimum or maximum. But the second derivative or the even derivative cannot classify the subtle points. You remember this? It's not important to remember, but just to have a feeling what we are doing is not far away with respect to what you did in gymnasium. In the university, we do something more complex, more probably, which we can not directly, but we can understand some programs, some application in economics, in production, something like that. We are working with the second derivative. In fact, in the exam, often is this the case, but not necessarily the unique case, minimum, maximum. Sometimes it's important to find if we move in one direction is the minimum, if we move in another direction is the maximum, at least in technical problems. But let me remain on this. The second derivative, in this case, is characterized by a matrix because we have x and y. Helps us to classify if this point is the minimum or maximum. As a gymnasium, the second derivative is, or in this case, something related to the second derivative, because here we have a matrix, something complex than the second derivative, even though we can see here, at least in this part here, second derivatives. But this row here and this column here characterize the hill side or the valley side. Of course, white, so we have to demonstrate the theorem. In the presentation, I told you about the theorem, which I will calculate. I will repeat again here. But in any case, this and this which is the same. This line is the transpose of this. Is there because we are considering the border structure. In fact, in this row and this column, we have the derivative, even though the first derivative, but of the constraint, which characterize the border, let me say. Okay, let me do the calculations. This is zero as a definition. Did you agree? It's put there. Of course, to understand exactly the structure here, we have to look at the theorem, but it's not so difficult to remember. If you don't remember, you can find the datasheet. The derivative of g with respect to x with minus y is minus 1. Because if you look at g, which is here, the derivative with respect to x is 1, with minus is minus 1. Why is minus 1 also here? Because the derivative of g with respect to y is also 1, with minus 1 is 1, is minus 1. With minus is minus 1, excuse me. I transposed, and I have this element here, these three elements here, in form of row, we have here in form of column. Don't care about that, you can find the datasheet. Now, this 4 element is something probably which you have seen in math 2 when you learn the Hessian matrix. Here we have the second derivative of L Lagrange with respect to x. Here we have the second derivative of L with respect to y. Here we have the derivative of x, and after the derivative of x, the derivative of y of L always. No? This element is equal to this. But if you don't remember, this is the derivative of L with respect to y, and then the derivative of L with respect to x. Extremely easy. Why it's 0? 0 because let me calculate this at the beginning. It's more complex. 2. Why is 2? It's not difficult to, because it's the second derivative of this expression. Right? The second derivative of this expression. The first derivative of this expression is this. It's the gradient. The derivative of this is 2. Clear? This is the first derivative. The second derivative is 2. Now, why this element is 4? This element is the second derivative of L with respect to y. Easy. The first derivative with respect to y is this. I told you before. This means if I do the derivative with respect to y, this is 4. Clear. Now, these 2 elements is easy to be calculated. Why that? Because as I told you, this is the derivative with respect to y of L with respect to x, the mixed derivative. This means if I consider this, which is the derivative of L with respect to x, if I do the derivative of this expression with respect to y, 0. Clear here? Look here. No? Here's the derivative of L with respect to x. If I do the derivative of L with respect to y, is 0. Here is the derivative of L with respect to y. Now I have to calculate the derivative of this with respect to x, which is 0 again. I think we have a theorem. The name is Schwarz theorem. That these 2 elements is always the same. The same. Now, the theorem says that I have to calculate the determinant. Yeah, how I can calculate the determinant? Do you remember fixed row? Which one? Here it doesn't matter which one, because all rows are characterized by 1, 0. Remember, I told you last time, typically we are considering the row in which we have more zeros in order to avoid calculations. Here is the same. Let me fix this. This means the row is 1. I mean, this I don't need to be calculated, because this element always multiply everything in this complex. Should I show you again the rule of the determinant? I tell you, it's easy to tell you than to explain. This element multiplies always everything. I mean, consider the first line, and then I will consider each element of the line. And each element of the line will multiply the rest. If this is 0, I don't need to be calculated. Let me show you here. -1, which is here, is up to 1 plus 2. Why that? Because 1 is the fixed row, and 2 is the second column. This element is characterized by index 1, 2. This is the coordinate. 1 row, second column. This means -1 up to 3, which multiply what? This element here, -1. Exactly now I can justify why I didn't consider this point here, because before doing these two calculations, one related to -1, this -1, and the second calculated at this -1, the difference is the index. I don't need to put because it's 0. This means I will have 0, which multiply -4. Why -4? Because do you remember the concept? I have to cancel this row and this column, and I have to do the determinant of the remaining minor, this element, this element, this element, and this element. This multiply this minus this multiply this. Do you remember the determinant of the minor? This means -4, because 0 multiply -1 is 0. Plus, now I'm moving the column. I'm here, -1 up to, in this case, 1 plus 3, because the position is 1, 3, which multiply what? Again, -1, the element itself. Now I have to eliminate this row and this column, and the minor is this here. I have to calculate the determinant of this minor. This multiply this, it's 0, minus this multiply this, which is +2. Let me say I do the calculations. Is -6. That is negative. Now the theorem says I have to multiply everything by -1 up to m, in which m is the number of constraint, one constraint. This means I have a +6. If you remember, if the second derivative, which is reflected in these calculations, is positive, we have a minimum. Because the first derivative is always increasing. Better to say, is increasing around the point. We have just one point. This means we have a global minimum in the sense. Too difficult? Too difficult? No.
Why do you multiply it with -1?
In this case, in both cases.
No, so it's you calculate -6 as a determinant.
Okay, yeah.
And then you multiply it with -1 again. Why?
I can answer in an easy way. This is the theorem. To understand the meaning of this -1, we have to look at the demonstration intuitively. I have to remember. The theorem says exactly, in fact, here I formulate as in a theorem. The theorem says that I need this -1. And the question, why the theorem says so, I'm not able to answer now.
Okay, so we have to do it every time. So when there are, for example, you don't have -4 and -2, instead 4 and 2, so you have 6, also positive 6, you multiply it with -1 as well, and then you have -6, and then it's a maximum point, right?
Yeah, but the key point is m, no? This is written, m is the number of a constraint. In case of two constraints, you have a positive.
Okay.
Now, the meaning of this minus, I have to think, but I don't remember. I don't remember now. In particular, why it is in a function of the number, but I'm sure about that.
Okay.
Yeah, sometimes we have to look at the demonstration. I formulate a problem, exam problem, and we stop, no? With the just with the formulation. Let me something easier. We discuss a little bit what we did last time, and then we will go ahead with another topic. Let me see. Did you see that? Yeah. Let me look. Look at it.
And
we take a rest, but before taking a rest, look at this. The cost function is exactly the same as before. Huh? The cost function is exactly the same as before. But the constraint is x equal 1. Extremely easy in the calculation, but the structure or the solution or the method is the same. I give you just this indication. It's easy because how possible to say we can figure out, in any case, we have a minimum because the function is growing up. Yeah? This means practically what I produce in X is one piece per day, one element per day. The question is how many Y I have to produce in order to minimize the cost per day. It's not different as before, but the calculation is shorter. The calculations are shorter. Okay, we take a rest, 50 minutes. I stop recording, and then we discuss this. I tell you something, and we will go ahead with another topic. See you in 50 minutes. Okay. Okay, let me start with this exercise. Then I will give you some exercise homework, and we will start with another presentation. Basically, I would like to introduce the problem of the mapping, before mapping, something related to the scalar product in more general sense. Look at this. Find the minimum. Quickly. Look. This is the Lagrangian function. We can see here the function to be minimized, combined using the parameter lambda with the constraint. The constraint was x equal 1. This means, remember, in the theory, we have seen g of x comma y, in this case, g of x, minus the constant, which is 1. Because the constraint was x equal 1. The picture is clear, no? X equal 1 in 3 dimensions is in a plane parallel to z, axis z, and parallel to y, axis y. This means parallel to the plane z, y. The reason is practical reason, but before I try to justify a little bit more in depth, thus in the definition of this plane in 3 dimensions, x and y don't appear. Basically, for each y and each z. X equal 1 in, let me say, in 2 dimensions is this line. Is this trace of the plane, which we can see here a little bit, going, let me say, going up, parallel to z, y. Do you remember before I try to justify a little bit intuitively, but it's independent. This is the base concept. It's independent with respect to x, with respect to y. This means for each z and y, or that y and z. If you want to go more in depth, this x equal y, one in 2 dimensions, is parallel to y. Do you remember in high school, x equal 1, x equal 1 is parallel to y if you don't consider the dimension z, because it does not depend on y. The concept is always the same. Here it's easy because you learned it at high school. No? X equal 1 is in a line in 2 dimensions parallel to y. X equal 1. If I write x equal 1, is parallel to y. Why that? In our concept, we have seen at the end as in the conclusion, because it's independent of y. For each y is always x equal 1. This means we say parallel to y. But now, in a more extended dimension, x equal 1 in 3 dimensions is parallel to zy plane. Why that? Because it's independent of x and y. We can so analytically as before do some considerations, but this is belong to the chapter of analytical geometry, or more advanced analytical geometry, which we have seen together. Okay, again, this is the Lagrange gradient. You have 3 components. The first 2 components are as before. This I don't need to be commented, but in any case, also a different example. The derivative of the derivatives should be known. I would like to say can be done. Here's a little bit different, but the derivative with respect to lambda is always the constraint in this form, x minus 1 with my minus. If you use this minus here, please pay attention. Some books, if you look some books, sometimes it's plus. It doesn't matter, plus or minus. It's in a combination. Because the idea is the gradient of the function is parallel to the gradient of the constraint. Parallel is independent of the sign. It's a constant independent of the sign. Okay. It's not easy to see. Let me show you a little bit better. No, it's not much better, but anyway, the gradient equals 0 reflects the derivative equals 0, as in gymnasium. No? We have learned that the derivative equals 0 represents, or using the derivative equals 0, we can find minimum and maximum, both. No? Could be minimum, could be maximum. This means in our extended dimensions, the derivative equals 0 means the partial derivatives equal 0. This means, as before, this equals 0, which we can find here. This second component, which is here, equals 0. And the third component equals 0. That is extremely easy to calculate. Because from this equation here, we have a y equals 0, clearly. And from the last one, we have x equal 1. This means for the last one, if you consider the first one, just plug it in, we have lambda equal 2. Clear. This means the point which we are looking for is x equal 1 and y equals 0. Let me show you the rest of the solution if I find. Oh, there is. You're looking for a minimum, no? It's clear. 1, 0 is our is extremely, but it's not different as before, just the calculation is something easier because we can see that here we have a 2, 0. Huh? Now I justify this border equation, the border matrix with ISM. Huh? We need just a calculation. This is 0 for the definition. Why this is -1? Because it's the derivative of G constraint with respect to X in this case with minus. No? But G was X minus 1. Huh? G was, the constraint was X. I show you. This is G. X minus 1. The derivative of this is 1 with the minus is -1. Here was the derivative of G with respect to Y. We don't have Y. We have Y. For each Y, which we want, we don't have Y in the equation. X minus 1 is G of X comma Y. This means 0. This means this is the row. I reflect the same row in form of column here in order to build this border concept. Here we have the matrices of the components of the minor of the second derivative. Here we have the second derivative with respect to X of L. No? This means it's the derivative of this, which is 2. Why the derivative is 4 as before? Yeah, I don't need to comment them. It's the derivative of this with respect to Y. And the second derivative of L with respect to Y. Here we have the first, the derivative of this, 4, which can be here. I already calculate before. Here we have the mixed derivative, let me say. Here's the, after the derivation of L with respect to X, we have the derivative with respect to Y. This means the derivative of this with respect to Y is 0. This must be the same. It came after the derivative with respect to Y, the derivative with respect to X. This means the derivative with respect to X of this is the derivative with respect to Y. No? First derivative with respect to Y. If I do the derivative with respect to X is 0. Now, the determinant considering this is the more comfortable or the more suitable because we have 2, 0. It's extremely quick to calculate this. It's extremely quick because I consider this element here. We can see I put everything together. Look, m -1 up to 1, -1 up to 1 in accordance with the theorem, multiply the determinant. -1 up to 1. Now look at the determinant. Why -1 up to 3? Because this element here is the element 1, 2. This means -1 up to 1 plus 2. If I eliminate the first row and the second column, remains as before this element, this element, this element, and this element. As a minor. The determinant of this minor here characterized as this is let me see, I see mistakes. No, it's correct. Let me see, I don't see. Oh, can I say mistakes? This is here. -1 up to 3. This is correct. No, it's correct because I have this multiply this minus this multiply this. I didn't put -0. No. This -1 is this element here. This -1, this element here. This -1 is fixed. This -1 is fixed up to 1 plus 2. This element here is this minus this, and I didn't put here -0 multiply 0. I don't need. The calculation, if I do all together, is positive because it's +4, which says it's the minimum. Reflects again, as in gymnasium and high school, the second derivative positive. If you remember, if the second derivative is positive, we have the first derivative is increasing. I don't know if you remember this concept. This means we are in this case. I don't know if you remember. This was x equal 1, right? The case was x equal 1. This point here is a point characterized by the first derivative 0 and the second derivative always positive around its neighborhood, around. But here is the global minimum. This is the global minimum. We don't have other minima. We have a global minimum. Second derivative positive means first derivative increasing. I don't know if you remember this. In this neighborhood, here around. I don't know if you remember. 0, the derivative at this point, but in all here around, the derivative is, first derivative is positive. Is increasing, excuse, is increasing. This means the second derivative positive. I can improve a little bit if you want. Let me see if I can add. I think this is enough for this. I will bit too. Should I do another exercise or we can proceed with another topic? I think we can proceed. Boring. Otherwise. Nevertheless, I will put some exercises. Sometimes they are a little bit boring. If you consider exercises with complex cost function to be minimized, in the exam will be extremely easy because I want to see just the concept. And believe me, if the function to be minimized is complex, always we need numerical methods. It's not possible to solve analytically, because if the system, which we have seen how to find the minimum maximum, is non-linear, well, God knows where is the solution, how many they are. I don't know if you remember, linear, non-linear, we'll come back on this. What I can say on this topic here. Let me tell you just one thing. And then I upload the file in my study within the lecture number 7, which we can do some more talk about a new topic consisting of, yeah, I would like to tell you something more about the inner problem. Then we will start remapping and we conclude the next week. Okay. You remember we have seen using, let me open the lecture last time, just in a sketch. About the key point of the lecture last time. Let me share. Why so slow? Yeah, do you remember here numerical methods? But I don't have time. But I would like to inform you if you need in your projects, contact me. I have a software. We implemented a lot of numerical methods for technical systems, but we can consider also for economical systems and so on. Therefore, last time I told you in the context of the discrete examination, we can think about something like that. Why not? We have seen something here, we will see. Okay, last time the key point of the demonstration was not a demonstration. No? But you remember this picture here, which I improved also with my slides. But basically, it's this equation here. The gradient of f is parallel to the gradient of g. Therefore, this lambda sometimes in some books is plus lambda, not necessarily minus lambda, because about the sign of lambda, if we say that two vectors are parallel, we don't need to discuss. Could be plus, could be minus. The calculation will give us the solution. The picture, better to show you this probably. I don't know if it's better. About the picture, I am not the best, believe me. But this was a little bit the explanation. Here's a little bit the concept, the explanation of the practical this picture I don't know. That in the maximum here, if you remember the idea is to climb on this hillside, and when the maximum meet the level curves, the gradient of f is parallel to the gradient of g. I have another better pitch. I don't know if it's better really. In the exam, don't worry. I don't ask graph. Now probably we can see a little bit better this. Let me sketch what I intend, but just in a sketch, because in any case, this concept here is the idea. Where the idea, let me say, to understand where the Lagrange come from. Remember, then I did the integral, and we justify a little bit this combination. But just a feeling. Look at this. If I have this f, x, and y, again probably the last time I emphasized, but I would like to repeat again. Also in my slides, isn't it? Where is? Here it's not very well, probably at the beginning. I emphasize at the beginning, I think. Yeah, it's not explicitly, but here say exactly what I told you. That at the minimum or at the maximum, we have this parallelismus. Basically, delta f of x10, x20, exactly at the minimum in x and y, is parallel of the gradient of g at the same point. Look, try to do at home this exercise. It's not so easy, but I sketch a little bit the idea. We have this function. Yeah. Let me calculate the gradient. Try to do at home. I sketch how we can do. If you consider now the level curve of this. Remember, for level, remember last time we have seen for level z equals c. C minus C minus C and see. Think about something which is growing up in this direction. If the zeta direction I cut at level C, remember the lecture last time. Over here, this level curves. I can represent the level curves in this form here. Let me show you in the lecture. Probably can be seen, but I'm not sure because what in my probably mine is also a little bit better, but you can see here. Also. Yeah, here. X and Y. Here the axis Z doesn't matter what. If the level instead of A is X, or excuse me, it's C as here. No, here's not. It's a little bit different than the notation. It's A. The notation, the level is A. I put A equals C. If you want, I put A. Probably it's better. A minus A minus A and A. Of course, the representation of the level curves is in the plane x1 and x2. In our case, is in the plane x and y. Think about something which is growing up. And if I cut at level z, if you like, equal a, this is the representation. Try to do at home, try to show at home that this vector here, which depends on x and y, is always orthogonal to the level curves. This means always orthogonal to what? To all possible tangent at the level curve. Because you remember, I told you last time, the concept of the tangent. We don't speak about an orthogonality with respect to the curve. It's unclear. We speak, or we define, the orthogonality between two vectors. But you remember, the vector or the vectors characterize line. Therefore, I told you when the hillside meets the level curves. Here, just in an interesting exercise, in order to show an example, as an example, that the gradient of this function here is always orthogonal to the level curve, could be this one. Of course, we have to calculate the general tangent here. It is not so easy, but try to do it next week as in a possible exercise in geometry, analytical geometry. I will show you. But the idea is, look, for instance, if you consider this curve here, or this tangent here, x equal a, excuse me, y equal a. Here it's trivial to show you that the gradient at this point here, with respect to this line here, the product it's zero. I show you, and also here, and of course, for this line here, x equal a. Of course, if you calculate the general tangent, this is the unique difficulty, and try to do it in order to remember. I told you there is a geometrical demonstration that the gradient is always orthogonal to the level curve. This could be nice. Could be nice to do it. And once we understand this, it's clear that in the tangent with the hill curves, as I told you last time, this can be seen now again from the picture, it's clear that the gradient to the level curves are parallel to the gradient of the constraint. And I show you again in the picture, but let me show you, let me say, if you want this example. Or if you want, I can leave you atom. Try to do if you want this. What I can say here more. I don't think so. Hmm. Yeah. Let me try to do this example here, and then we will discuss together. Let me see. Next time I will do the calculations for you a little bit to show you this. Okay, today is also enough what we have seen, but we will come back a little bit also next week. Let me open. Should I upload in my study or after the lecture? What do you prefer? After or directly now? After the lecture, so we can go ahead. So in any case, it's nevertheless, I will come back a little bit on this concept of the maximum minimum, because sometimes is one of the most difficult topic, in my opinion. Now we will see this is something which you already discussed, is a little bit more intuitive also. In this chapter here, we will see a little bit some short repetition of it, extremely short, about the some concept which you have seen in terms of vectors. I will extend in linear space, but very important. We will see an extension of the inner product or the scalar product or the dot product, let me say. And then I hope to start with the mapping. The mapping is extremely interesting because I will introduce the linearity and then, yeah, something about these correspondences, nullity, rank, and next week we will conclude also with this topic. I give you some homework. Let me start quickly, very quickly, with this linear space, which basically is in a repetition. Therefore, I need just a few minutes. It's in a repetition what I told you regarding the vector space. Here is more general. Do you remember? We have seen what the vector space is. I told you some properties. Here, linear space is more general, because we are not considered just vectors. Do you remember? At the beginning, I told you we have two vectors, x and y. Exists another vector which can be considered the sum of two vectors. Do you remember this? You don't have to remember because it's not important for the examination, but I don't know, probably the first lecture, I defined the sum, I defined many operators. Now, this kind of operators properties can be extended for any kind of mathematical entities. Could be functions, could be, I don't know what, anything can be considered in the context of this linear space if some axioms are satisfied. But we have seen already these axioms. I don't know if you remember. X plus y equals y plus x. At that time, we have seen with the vector. Vector 1 plus vector 2 equals vector 2 plus vector 1. Now, if you have two functions, function 1 plus function 2, it's clear. I define, or I consider the axiom. What an axiom is clear. It's in a sentence which I assume to be valid because evident, at least in the context of what we call linear system or space. Better to say, x plus y equals y plus x is something which you don't need to, it seems to be evident. Oh, so this one, For instance, x plus minus x equals 0. Existence of a negative element, existence of 0. I think this property we have seen quickly for the vectorial space. Linear space means the same structures, the same axiom, the same property, but more general. This means not only for vectors. In particular, for us, we are here for in mathematics for functions, with elements of a set. And then we can see that we have property which you already see. For instance, this associative, distributive. I don't need now to repeat, extremely boring. It's intuitive. In fact, when we speak about linear space and not vectorial space, we want to consider different elements, not only vector. Also for the vectors, everything is true. We have a valid. We have already seen. Look at this. Exam exercise. Directly, without many words, it's more interesting to look at this exercise. As I told you, the vector space is a specific form of linear space, in particular form. These properties can be valid, can be considered valid for any, let me say, mathematical structure. Or at least, if it's valid, we speak about a linear space. Look at this example. We have a set of a function, polynomial function, element, not vectors, element, mathematical element, functions. Moreover, polynomial say to you something, no? Polynomial. Function, forget polynomial. 1, t squared, t up to 3. 4 elements, not vector, mathematical element. T is belong to R, not is new. Question. Is function f of t 3 plus 2t squared plus undivided 3 multiplied t linearly dependent in V? Now, if all these properties, which became from axioms, are valid also for mathematical elements, of course, I can work in the same way instead of vectors with functions. I can pose the same question. Remember, as an exam exercise, I put a set of vectors. I asked you, are dependent, independent, but everything was based on these axioms, on properties, which I already introduced. Now, assuming that we know everything, but we consider different elements. Is the function f equals 3 plus 2t squared and so on dependent or independent in this set V? Extremely easy. The exam exercise is extremely easy because I have to find a linear combination of this element here which generates this function here. This means a multiply 1 plus b multiply t plus c multiply t squared plus d multiply t up to 3 must be equal to this one. If I find, if it exists, let me say if I find this parameter a, b, c, d, I can say that this function here can be generated by this element of the set. Remember the concept generated, dependence. I insisted with this word. Can be see practically this function here, something as a possible combination of this. Let me show. A equal 3. So I cover this element here. Ready? Extremely trivial. Because I have to apply the identity principle. I didn't tell you the identity principle is written in these axioms, but we know it's intuitive. It's a primitive concept. A equals A. Nobody asks why. This means if I consider A, here is a little bit, I try to go really fast. A, B, C, D must be real, but this is key. A equals 3. What about B? 1 divided 3. Because B is the coefficient which multiply. It's clear what I am doing. I am comparing this expression here which is general expression, and a linear combination of all these elements here with this particular f, because the question is the function so defined linearly dependent or independent? You can formulate, you can write as you want. In V, it's clear the question. Think about what we have seen in the vector. B equal 1 divided 3. What about C? The coefficient which multiply t squared. This is enough to consider C equal 2. What about D? I don't need t squared because we don't have here. This means I found. Now, the elements or the coefficient. I am asking you, is dependent or is independent? Is inside V, is reflected inside V or not? Can it be seen as a linear combination of the element of V or not? Yes. This means it's dependent. Because if I choose this element exactly in this form here, I see that this function here can be generated by the set. Think. Is this difficult? We extended the concept of linear dependence and linear independence at the function or set of the functions. It's easier than vector if you want. But vector is you have a component. Please pay attention. I can also extend in function vector of functions. The first component of a function, second component of a function. We say fields. We don't do in this exam. But think about in some problems, we need some structures more complex. But just to inform you, I'm not so bad. I don't ask in the exam. Vector or function. Each component is in a function. But we work very often with some forms. Let me introduce in a definition. A finite set S of element of a linear space V is called finite basis for V if S is independent and spans V. Independent is clear what I intend. Spans, you know the concept of spans? I didn't use this word before for sake of brevity, but spans means cover all V. Let me show you what I intend. It's in this, I don't remember if I introduced in the concept of vector, I don't remember, basis. But let me show, it's extremely easy. Yeah, I introduced but very quickly. Probably I didn't call span basis. But let me read this property. V is in a finite dimensional linear space, then every finite basis for V has the same number of elements. You remember, I told you in the context of the linear dependence and independence, when the dimension of a vector is larger or less of the number of the element in the sets. But now let me concentrate on this. Look at these two sets, V1 and V2. We can say that V1 and V2 are the same element in the sense of basis, because I can generate any polynomial of order 2. Even though here I have 1 and then I have 2, here I have 2 and here I have 1. But I have basically the same elements. Because both V1 and V2 span the same set of polynomial order 2. Cover, I can write with this element here, with this element here, or I can generate any kind of polynomial but order 2. Let me show you if I have something more interesting here. Here is yeah, we want to do this. Let me see if I have something more interesting. Okay, let me do that. It's easy. If I ask, examine the exercise with the solution. I have this set here, 1, 2, 2t. 1, excuse me, t, comma 2t. This is not a basis. If I ask, is it a basis or not a basis? The answer is not a basis. If I'm thinking about the order 2 as before, no? Basically is connected this exercise with this one. Because I cannot generate a polynomial order 2. It's easy. Because the polynomial order 2, or the element order 2, is enough to show you this. Cannot be generated by these 3 elements. This means these 3 elements are not, or the S is not a basis for a linear space characterized by the polynomial order 2. Think about if the set S isn't a basis for the linear space of polynomial order 1. Think about it. And think about that this, to answer this question, independent. In this sense, is not, because we have 2 elements which is not independent, t and 2t. But of course, I can eliminate 1. But formally, is also not a basis for in this form here, because they are not independent. The elements. But just the formal thing, because I can consider, I can eliminate 1. Let me now introduce another topic. Do you remember we have seen the dot product? I don't need to explain again. This was the definition of the dot product between 2 vectors, x and y, characterized by n components. Both must be characterized by n components. And the dot product associate to x and y in the context of the dot product and a scalar, which is given by the product of the corresponding component. We can see here, no? xi multiply yi. We have seen also a couple exercise, dot product. Now, I would like to extend the concept. I would like to extend the concept to the inner product, which is more general, inner product or scalar product. The dot product is in a form of this, just in a particular form. We already seen that this basically is applied for vectors. Now look at this. About the definition is repeated here. I also say in scalar. And let me also repeat this property here, which we already seen, symmetrics. X scalar product or the inner product y equal y scalar product x. It holds also for this particular form of the inner product, dot product, scalar product. It's the dot product. Again, dot product is in a particular form of inner or scalar product. Look at this, and then we will insist later about this. We have seen also this, but in a very short form. What is the concept of the linearity? It's basically expressed here. And the dot product reflects, guarantees or satisfies this property here. But in general, each inner product, each scalar product must guarantees these properties. Linearity, and then I would like to insist on this, means we can see from here that I can distribute. This we have seen during the when I introduced the dot product. I can let me say distribute. We called at that time distributive the product between x and y and x and z in this form here. A multiply x dot y or scalar y, because here we are speaking about inner or scalar product. Dot product just in a particular form. Again, B, which multiply x scalar z, which A and B are reals. And here I introduced also the homogeneity property because I have some constants. I have some constant. If you don't have the constant, if the constant is equal 1, we speak about just the linearity, if you want. This separation, this distributivity, if you want. Non-negativity, we have seen that x dot x, or in general, x scalar x is positive or 0, 0, if and only if x equals 0. Examine the side. Let us define this dot product, scalar product, excuse me. This scalar product in this form here is in a definition. It's not the dot product, because dot product can be defined for vectors. Remember the sum of the product of corresponding component. If you have two functions, x and y, we cannot understand what the components are. No? I have to associate a scalar, and I have to be guarantees these three properties. This means I can define this form. I don't know if you remember. The integral of x multiply y equals the integral of y multiply x. The integral is in a linear function. I don't know if you remember from math. The integral of x multiply x is always positive. In this case, it is 0 if this is 0. Huh? Or at least in the yeah, can be the positiveness. I would like to say, of course, depends on the choice of A and B, but A and B belongs to the definition. I mean, I have to declare what A and B are. I have to declare what A and B are because at the end I have to obtain the results in scalar. We can see here. I mean, I need in a scalar. This means A and B make the differences. For instance, if positive or not. But let me come back on the question. I have an effect on the set V. The question is now calculate A and B such that function 1 scalar t equals 0, function 1 scalar t squared equals 0, function t scalar t squared equals 0. I don't know if you remember, using different A and B, I can obtain some orthogonality if I need. Okay, let me show you the results. One scalar B, in accordance with the definition, is integral from A to B of 1 multiply t in dt. The integral of t, I don't know if you remember, is t squared divided 2, calculated between A and B, which is equal b squared divided 2 minus a squared divided 2. Gymnasium. I don't know if you remember. A little bit. When we have, in this case, 0, we have in this case 0 if A equal minus B, but also if A equal B. Now, if A equal B, this is trivial. Because A equal B, I annihilate the integral, but A equals minus B makes sense. This means, yeah, I have to consider an symmetric interval to obtain the orthogonality between these two functions. Excuse me. The exercise is just to give you the possibility to understand that the scalar product depends also on the definition of the interval in this case. If this is the let me say is the scalar product. I don't know if can be also A and B plays an important role in the context of the definition of the inner product or scalar product. Because yeah, the scalar product is a bit more complex. Also, if you think about this property here. This is not a problem, but here is positive depending on the interval, just to have just a feeling. Try to do at home, or to show at home, this is the idea is going to say the scalar product between 1 and t squared, between A and B, doing the integral from high school, we have this expression here. And here we can see just the trivial solution, just for the trivial solution, A equal B. This means to annihilate the integral, we have the orthogonality. This means 1 and t squared are never orthogonal. And never orthogonal. In this case, we have the orthogonality also not a trivial way. Try to do this at home. When doesn't exist, we have also here the solutions. Just the idea is to understand that depends on the interval. Let me go ahead now with the mappings. That is interesting. It's not so boring as before, I hope. We are speaking about a mapping T from a set V could be in a set of vector, could be in a set of function, to another set of W. And this means T from V to W. Very often we write here V capitalized to be W capitalized, but here it seems to be related to elements. I copy from a book. Or by X to Y equals T of X. Basically, it's in a function. It's an association. It's written here. It associates exactly one element of Y, which belongs to W, for each element or for each X. It's in a function. Just one and only one element of W is associated. V is called domain. I don't know if you remember from school. T of X is called image of X. Very important. We come back on this. Considering T O under T. In other words, we say that T maps X into Tx. This means maps equals functions. Corresponds. Not is new, it's just a new word. Now, I would like to insist now on linear transformation, including here, again, the homogeneity, because we are considering alpha and beta. Let V and W be linear space over the same scalar field. And yeah, linear space, I told you with these axioms, which I defined. And we have the unique, the same scalar product. I define the same scalar product. And the mapping T on the function T from V to W is the linear function if, look at this, is more general as before. T applied to alpha X plus by equals alpha, which multiply T of X plus beta, we multiply T of Y for each X, Y, which belong to V, and for each alpha and beta belong to R. We can see here, we summarize homogeneity because of this alpha, let me say, come from the transformation. And I distribute the transformation. Basically, it's a combination between the distribution. which you can see here, of t with respect to the sum. And this homogeneity, which basically consists of putting in evidence the parameter alpha and beta. Let me do an example exercise. It's easy to do than to do. In your opinion, is t defined from x to x in a linear map or the linear function map equal function? No, I told you. Or not? Yeah, it's already the answer. Verify, that's not the answer. Basically means is linear or non-linear in your opinion? I have to verify this condition here. We can see that is valid, and I have also the solution. Look, t of it, I have two elements, x1 and x2. And according with the map, I have 2 times x1 plus x2. Now, this expression here can be seen that x1 equal to x1 and tx2 equal to x2. Because I can distribute, if you remember, in high school or like elementary school, this multiply this plus this multiply this. This means tx1 plus tx2 is equal t of x1 plus x2. Can be seen in a different form. Tx1 plus x2 equal 2 times this here. Tx1 is 2 times x1. Tx2 is 2 times x2. And then we can see that tx1 1 plus x2, this here, which is here, is equal to tx1 plus tx2. Easy. I don't need to... Look at this. This is more difficult. Is linear or not linear? This is more difficult. Is linear or not linear? Is not linear, but almost linear. We say this is affine, linear affine. We have to verify this. This is true if t is in a linear map. Look, t applied to x1 and x2, t applied to x1 and x2 is 2 times x1 plus x2 in parentheses plus 1. Please pay attention. T applied to x1 and x2, t applied to x1 and x2, this means 2 times parentheses x1 and x2, parentheses plus 1. This is exactly when I have two elements which are working together. Now, if I have a separation between two elements, tx1 equals 2x1 plus 1, always in accordance with the map, and tx2 equals 2 times x2 plus 1, if I am considering separation between the two elements. Basically, if you think about this concept of the linearity reflects exactly the superposition principle. We have two causes, x1 and x2, and we have two effects. This means if the system is linear, if the two causes, x1 and x2, act together, we have the same effect if the two causes work in a separate form. Should I do an example? Breathe. I am here alone. 1 hour, I breathe. I consume I don't know how much. The system breathing is linear if two persons, at this stage, because the person could be different. Let me, the same person. I am still here half hour, then I come back here for another half hour, but the sum of these two phenomena separated, I don't know if it's a good example, but intuitively we can understand, equals the sum equal when I have the effect together. Another better example, I have just example in electrical systems, but intuitively we understand. We have two causes, which in one case work together in phenomenon characterized by T, transform. I have in mind this brief, but probably it's not the best. That could be. And then I separate the causes. I look in this transformation if the effect considering separated causes equals the effect considering the two causes together. We can see that it's not linear because here, if I'm working together, it's not equal if we are working separated. Because here we have 1 equal 2. It's not the same. But this is almost linear because if I don't know if you remember in high school, this kind of function we can consider in translation. No? We can consider in translation. And then we can consider the function translated at the point -1. And in this case, basically, it's just linear plus isn't a constant. But anyway, theoretically, it's not a constant. It's not linear. More interesting, this one. Is linear or not linear? As I told you before, this is not linear because intuitively, this separation holds just for x up to 1, the elements up to 1. Here's the demonstration. When we are working together, if you remember this binomial exponential rule, we have this one. When we are working separated, we have these two results, but of course, this here is not equal to this. We learned at school. A plus b squared is not equal a squared plus b squared because it's not linear. This reflects the not distributivity of the exponent. Now, with this example, we have in mind a little bit better what a linear function or transformation or the map is. Let me go ahead. Let me skip this exercise. Let me go ahead with the nullity. And then in the last half hour, I will upload, I will open another lecture. Nullity and rank. Definition of null space of a transformation or on a function if you want. I have a transformation T from V to W. The set, please pay attention, N of T, null of T, is called the null space of T if X such that X belong to V in the domain T of X equals 0. Is easy. This means all X which belong to the domain which annihilate the function. We have an easy property. Every linear transformation maps 0 to 0. But if in a transformation map 0 onto 0, not necessarily linear. The case of x squared map 0 into 0. X squared map 0 into 0, but it's not linear. In this sense, this property states the property just in one direction. It's just a necessary condition. Every linear transformation necessarily map 0 onto 0. But it's not enough to characterize the linear transformation because x squared map 0 into 0, but it's not linear. We demonstrated. This means this property is just a necessary condition for the linear for the linearity, but non-sufficient. The example is x squared. X squared maps 0 into 0. It's clear, huh? X equals 0, x squared equals 0, but it's not a linear transformation. It's necessary condition for the linearity, yes, but is not sufficient. This case here is clear also. It's not linear. Necessary condition, we can say when is not. You remember I told you, a necessary condition says to us when something is not something. But it's not enough to guarantee the linearity. Look at this. This maps 0 into 0, but it's not linear. Again, the property that 0 mapped into 0 with respect to linearity is just necessary, is not sufficient. Understand what I intend? Just to, we conclude with this presentation, consider the dimension, then I have 20 minutes. I would like to introduce, the presentation more interesting to do some exam exercise today. Then next week we go in depth on exam exercise. The definition of dimensions. The dimension of the null space n of t, which is element belong to the domain, we guarantee that t of x equals 0, is called the nullity of t. The dimension of the range of t is called rank of t. Range is the image. Do you remember I told you the image? Exactly before, W. It's an image of a function. I will come back on this a little bit later. Sometimes collection. More than definitions, this is more nomenclature, if you like. But in fact, I didn't wrote the definition, but okay. Very important this, and then in the next slides, we will go in depth. We have a theory which says that if the dimension of V is finite, this is easy to understand because we are working just with finite dimension, then please pay attention now. Dimension of the nullity of the null space, if you want, plus the dimension of T of V, this is our image, if you want, the dimension of the image. Remember, I told you before, TV is the image. This means the dimension of the image equals the dimension of the domain. V is the domain. I don't know if you remember. This means if I have a transformation, everything which is in the domain will be projected, let me say, or will transform into null and into the range or image. Let me open the last presentation of today and let me show you some exam exercise and some aspect more in depth. The lecture number 8, I will upload both lecture at the end today. Exam exercise. Try to do this. To do this. Exam exercise. Calculate the linear map. Everything is linear here. This means the map. T from R up to 3 to R up to 2, such that T112 into 13, T121 into 00, and T100 into 11. This is difficult? This is difficult.
Yeah, I don't know.
Okay, we have an indication nevertheless. This is an indication which basically try to write explicitly this information here, which nevertheless is also included here. But look, we have a transformation which transforms element from R up to 3 into R up to 2. We can see from here. element which belong to R up to 3, this element belong to the space R up to 3. We have 3 components. This element 2, this element 2. This T maps 1, 1, 2 into 1, 3. An element, a particular element of R up to 3 into R up to 2. This means, more in general, that the transformation T is characterized by X, Y, Z, which belong to R up to 3, in this form. A multiply X plus B multiply Y plus C multiply Z, comma, D multiply X plus A multiply Y plus F multiply Z. Why that? Because we have 3 elements, A, B, excuse me, X, Y, Z, in linear combination, because we have a linear map, even though if I don't write linear, we are in the concept of linear. And we can see that the linear combination of element X, Y, Z are, let me say, have, probably better say, the image in 2 dimensions. We can see this first component and second component. The goal is to find A, B, C, D, E, F. But it's not difficult because we have the conditions. Look at this. I am writing A plus B plus 2C equal 1 and D plus E plus 2F equal 3. Why? Easy. Because I have 1, 1, 2, which is mapped in 1, 3. 1, 1, 2, 1, 1, 2 is mapped in 1, 3. If you look at this expression here, which is something more explicit than this expression and this expression, now it's quite clear why this linear combination equals 1, 3. And I can do the same here. If you look at 1 to 1 is mapped in 0, 0, I will upload in my side. I have exactly 1 to 1 mapped in 0 first component, 1 to 1 mapped in 0. Look at this, extremely easy. 1, 0, 0 is mapped in 1, 1. A equal 1, D equal 1. Because if you look here, we have just A will survive. Because this will be not there, this will be not there, well, just D will survive. Try to do at home the calculations. Can be seen also in this form. This probably, I don't know if you like this form here or if you like in this form here. Row multiply column, row multiply column, row multiply column, can be seen also in this form. I will come back on this. This is just at this time a little bit to introduce. Let me do this together. Next week we will do a lot of exam exercise, but try to do this again at home. Now here together. Given A in a matrix, which states in a transformation. Why in a matrix state the transformation? Because we can see here, let me see if it's clarified a little bit here. Yeah. Why in a matrix states in a transformation? In a matrix state in a transformation because, let me, because at this moment, I told you about the zero or the null of a transformation. The matrix A, let me copy. This is state transformation because I can write in this form. I will transform X. Excuse me, I didn't. Yeah, I don't know if I. Okay, yes, already, no? I will transform X, Y, Z in a space of 2 dimensions. If you want, I can. Or let me write as before. Probably it's better to write as before. Zero, no? Excuse me. Zero, I copy wrongly. It's the transformation between a space R up to 3 into R up to 2. In some books, you can find also something like that, as before. What I told you before, something like that. X, what I told, T of X, Y, Z, such that T of X, Y, Z, transform X, Y, Z into X plus 3Y, comma, 2X plus Y plus Z. If the transformation is defined by this matrix. This I told you before. No? And we come back next week. Now we have just 10 minutes. We will go in depth. But this means, we will see more in detail next week, that in mathematics, in the matrix, defined nevertheless in a transformation. Look, if the question is calculate the null of T, which is equal to the null of A, because we have that the transformation T can be represented by a matrix. I explain a little bit better now. No? What is the null of the transformation between R up to 3 and R up to 2? Is everything which annihilated the transformation. This means which annihilates the matrix A. Look, you can write X, Y, Z, or you can write A, B, C as you want. No? Yeah, I use A, B, C instead of X, Y, Z. I don't know why. This means this multiply this, row multiply column equals 0, row multiply column equals 0. This means from the first row multiply column, I have A plus 3B equals 0. Because 0 multiplies A is 0. No? This means A equal minus 3B from here. If you consider the second row, we have 2A plus 1B plus C equals 0. This means plugging in A here, we have it minus 6B plus B plus C equals 0. This means C equals 5B. We can see now that we have the null I called this null X. Probably this is the reason why I didn't use X, Y, Z, because X is the set of elements characterized by A, B, C, the domain, which annihilate the transformation or the matrix. We can see here A equal 3B, the element is A, B, C, no? A equal 3B. B, because we don't have B condition. This means for each B, no? This conditions, these two conditions for each B, B and phi B, because C equal phi B. I can put in evidence B. Do you remember that the property of the vector or of this element here? B, which multiply minus 3, 1, 5. This means for each B multiply minus 3, 1, 5 as a vector, I annihilate the transformation characterized by this matrix. Look at this. I have a transformation from R up to 3 to R up to 1. We can see from here. I transform A, B, C in a scalar. I don't know if it's visible. Rho multiply A, B, C. The result is a scalar. Because we have 1A plus 3B plus 0C, which is a scalar. This transformation is from R up to 3 to R up to 1. It's difficult? A little bit, eh? Should I show you here in the lateral camera?
Yeah.
The matrix which defined the transformation is this. But this can be seen in this form. A, B, C, no? We use. Transform A in a transformation. This matrix here can be seen as a transformation from A, B, C, which transform A, B, C into A plus 3B, comma, no, can come, excuse me, directly. This means from R up to 3 to R. This is a scalar. I forgot, there's no comma because we have just one row. This is a way to represent a transformation using a matrix. Of course, I a little bit skip some definition. It could be this is the problem, because I would like to, at the end of next week, that we have just one block to repeat more in detail, but I would like to anticipate some. Yeah, look, exactly what I wrote. Now, if I look for the null, this means I have to find the set of ABC, which transform everything into 0. The codomain, the image, better to say, the image is equal to 0. This means A plus 3B must be equal to 0. This means A, for instance, please pay attention, for instance, A equals minus 3B for each C. But this means can be written in this form. The null of A minus 3B, because A equals minus 3B, B and C can be seen in this form. Because you have two parameters free. Here B is free, and in particular C is free. This means minus 3, 1, 0 is going to 0, no? But we can see here 1 multiply minus 3, plus 3 multiply 1 is plus 3, 0 multiply 0 is 0, plus 3 minus 3 equals 0. Also here, 1 multiply 0 is 0, 3 multiply 0 is 0, 0 multiply 1 is 0. We have a set with dimension equal to, which is characterized by these two generators. Basically, we have a plane which annihilate this transformation. All elements which belong to this set characterized by these two vectors annihilate this transformation. Last exercise, try to write, and then we will check together. We have a transformation characterized by the matrix A. As the matrix 3 times 3. This means the transformation is 3 times 3. As before, no? Do you remember here, the transformation was 3 times 1, or the 1 times 3, better to say. 1 times 3. The domain is three dimension. The transformation went from R up to T to R up to 1. This means I have to find ABC, which transform everything into 0, 0, 0. We have to find ABC, we transform everything in 0, 0, 0. Extremely easy. I have to find ABC, we transform everything in 0, 0, 0. The null, no? Annihilate the transformation, which is characterized by the matrix. Look, A plus 3B equals 0. A plus C equals 0. A equals 0. If A equals 0, C equals 0. If A equals 0, B is equal 0. We have just 0, 0, 0, which annihilates the transformation. This means the dimensional is 0, because one point at dimension 0. The same here, no? The same procedure, but not the same results. Look, R up to 3 to R up to 3, calculate ABC, which annihilate the transformation of the matrix. Transformation equals matrix, or better to say, a transformation can be represented by a matrix. I showed you this. Row multiply column, I have A plus 3B equals 0, which imply, I didn't do any transformation, but here A plus C equals 0, which implies A minus C. 2A plus 6B equals 0. Look, why this is the solution? Let me see. We can see from here A equals 3B, right? A equals C. We can see here, no? There is an error here. A equals minus 3B, I see here, no? B is okay. You see? No, it's okay. It's okay. Because here we have that C is equal 3B from here. I don't know if it's visible. A is equal minus 3B. But C is equal minus A. Everything is okay. B is free for each B in this set. Of course, can be written as another form, but the solution is equivalent. I can choose also as free A instead of B. I don't know if you can see them. You can choose whatever you want as a free parameters. The dimension is 1. This means we are on a direction which annihilates the... Okay. I already introduced this, but as I told you, next week I will go in depth. The matrix is associated with the transformation. We already see with the matrix, I can represent the transformation. Next week, we conclude, I do exam exercises. I don't know if I will consider this, probably yes, because it's very short. But in any case, I will tell you again about this matrix associated to the transformation, and we have just one block. I will do exercise on maps. I think I have one block. I will dedicate it to the exercise, exam exercise.
Ja, wir wollten ganz gut sagen, wir haben nächste Woche kein PR. Es wird wahrscheinlich auch keiner von uns hier auf dem Campus sein. Der nächste Woche komplett online sein.
Yeah, I can do online for you. I will send an email to everybody so that everybody knows that we will meet online. For me, it's okay. I am in campus, but if you say it's not here, it could be that I think that should be here, but in any case, I can remain in my bureau, in my office, or where I am without moving. For me, it's also okay. I think I have a meeting in the afternoon. This means I am here. If something want to speak with me. But it's also for me, if you are not here, I can do from my bureau without coming here, without organize everything. Okay, thank you for your attention. I'm here for you if you want to ask me question next week from home, let me say, from directly online. We will do exam exercise on maps. I will repeat what I already introduced, this mapping equals or equivalent to matrix and so on.